Now we move on to our step number 2. In this step, we're going to prove the upper bound for the radius. Specifically, we'll show that r is less than or equal to the square root of n over k for any ball centered at the origin with radius r contained in this cube of set length 2. Now, let B be any ball centered at origin with radius r, be any ball that is contained in this cube. In order to study this ball, we're going to give it a parameterization. To help you understand this parameterization, let me draw a picture. In this picture, k is equal to 2 and n is equal to 3. So we're going to give this two-dimensional disk, two-dimensional ball, a two-dimensional parameterization. Specifically, we're going to choose a map that is linear, carrying the k-dimensional ball in Rk onto this k-dimensional ball in Rn that is contained in this cube. So that M from Rk to Rn be a similitude carrying the unit ball in Rk to this given B. So here we identify this map M with its matrix representation under the standard basis of Rk and Rn. Now, what do I mean by similitude? By this I mean M is a linear map and isomorphism onto its image M of D 0, 1 equal to B. B is this ball. And for any x in Rk, this M is going to dilate this vector to R times that vector. This is what I mean by similitude. Now the hypothesis, the condition that B, this ball, which is the image of M, being contained in this cube means that for any y in the unit disk in Rk, that each coordinate of the vector my must be bounded by 1. Recall that in matrix analysis or function analysis, this maximum norm means the maximum of the absolute value of all of its components. So this condition precisely means each component of my must be bounded by 1. So this condition precisely means the absolute value of each component of my must be bounded by 1 whenever y is in this unit disk in Rk. And using the language of function analysis, you can further translate this into the statement that the operator norm of this linear operator M from Rk with two norm, the standard Euclidean norm, which corresponds to this disk, to Rn with the maximum norm or supremum norm, which corresponds to this cube, is bounded by 1. Or you can use the fancy notation saying that the operator norm of M with respect to the 2 norm and the infinity norm is bounded by 1. And using this statement, we can transform this problem into a problem of functional analysis or matrix analysis. So this is equivalent to finding this quantity, the supremum of the operator norm of M with respect to the 2 norms on Euclidean space, where M from Rk to Rn is a similitude, and the operator norm with respect to 2 norm and infinite norm is bounded by 1. Note that this part corresponds to this R, because M is a dilation by a scale of R. It sends this unit disk, unit ball, to a ball of radius R of the same dimension. And this restriction comes from here. So this problem is equivalent to our original problem. But to those people who are not familiar with the language of functional analysis, I should say this part is not really essential to the solution of this problem. If you don't understand what I'm talking about here, it's okay. We don't really need this language to solve this problem. Okay, now let's go back to this elementary statement. Now, if you assume that the matrix M takes the following form, it is the n by k matrix. It's a tall, thin matrix in the case when k is less than n. And we can write it in the block form. Here, V1 is this vector with components V11 through V1k, and Vn is a vector whose components are Vn1 through Vnk. Because I usually use column vectors, so I use the transpose here to mean that they are now row vectors. Or in other words, we can write MT as the matrix whose column vectors are V1 through Vn. Now if you look at this statement, it will be equivalent to saying that for any I, whenever the 2 norm of y is less than or equal to 1. This part corresponds to this part. We have each component of my. In this setting, it is Vi transpose times y, absolute value, less than or equal to 1. I should move it to here. And this statement is further equivalent to saying that for any I, the 2 norm of Vi is bounded by 1. Why is it so? For the forward direction, you can just take, because this y is arbitrary, as long as it is bounded by 1 in 2 norm, you can just take the vector y be the vector vi. And that gives you the right hand side immediately. And for the backward direction, if you have for any I, v sub I has 2 norm less than or equal to 1, then this part follows from the Cauchy-Schwarz inequality. And now we have transformed this statement to a much simpler statement about the matrix M. And now, since we know this M is really a dilation, you can write it into the inner product form for all x in Rk, because M is a similitude, so dilation by R. And if you write this back to the matrix form, you have xt mt m x equal to R squared xt times x. And now we are ready to show the upper bound. Take x as a canonical basis of Rk. Let x be E1, E2 all the way to Ek, and plug it back to this equation. We have, remember that M applies to E sub j will be the jth column of M. So we have v sub 1j squared plus dot v sub nj squared, the sum of squares of the jth column of M is equal to, right hand side is R squared. This is for any j from 1 to k. And now we sum up both sides for j from 1 to k. For the left hand side, we get k times R squared. Now using this equation we just derived, R squared is equal to this sum. So this is k times I from 1 to n of v sub ij squared, which is equal to this double sum. And we can switch the order of those summations. We first sum this up for j equal to 1 to k, and then I equal to 1 to n of Vij squared. Each of this sum will be bounded by 1. Because of this condition being equivalent to this. Each vector v sub I 2 norm is bounded by 1. So this kr squared is less than or equal to n, which implies that r is less than or equal to square root of n divided by k. And this proves the upper bound and finishes the step number 2.